Okay, so we're told here a rectangular coil is placed in a magnetic field. The coil has 40 turns of wire. Each turn is rectangular with a length of 0.06 meters and a width of 0.04 meters. We're told the field strength is 0.05 teslas and the current running through the loop is 1.5 amps. We need to find the forces on each side, find the torque on the coil, and then find the direction of the rotation. Okay, so we're going to draw a diagram for this because the length and width have to be manifest in a very particular fashion. So we have a permanent north over here. We have a permanent south over here. So immediately we know the field runs from north to south. We've got our loop sits in here. Let's imagine it's a square loop. It goes off this way. The current, we are told, runs in this direction. So we're given the direction of the current in this particular question. We are told that the length is 0.06. So that is this dimension. And then the width is 0.04. That is this dimension over here. So find forces on all sides of the loop. Well, if we think about this, the magnetic field affects all of the wires contained within the field, but it only affects two of them with any net force. It affects the wire on this side, which we might call AB, and the wire on this side, which we might call CD. So we've got AB and we've got CD. They will have forces on them. So first we're going to think about AB. We can use our formula for the force on a wire in a magnetic field. So we're going to use force due to a magnetic field on a charged wire is the length of the wire times the current times the field times the sine of the angle between the wire's orientation and the field. So we know this is going to be 1 because it's 90 in this case. This implies the force on wire AB will be equal to its length, which is 0.06 meters, multiplied by the current running through it, which is 1.5 amps, multiplied by the magnetic field, which is 0.05. This gives me 4.5 times 10 to the minus 3, and this will be newtons. This is for one wire. We have to remember the question told us there are 40 turns of wire in this loop. So we have to multiply this by 40, and this gives us a total force on side AB is actually equal to 1.8 times 10 to the minus 1. 1.8 times 10 to the minus 1, and this is newtons. So this is our first value. Because both sides are of equal length, they both sit in the same field, they both have the same current running through them, the total force on CD, so total force on CD is actually going to be the same. It's going to be in the opposite direction, but it will still have a magnitude of 1.8 times 10 to the minus 1 newtons. So when the question asks us to find the forces on each side of the loop, these are the only two forces. Right? The back wire, BC, doesn't experience any because the current runs in the direction of the field. The same is true for the sections of wires from between A and D. They run in the direction of the field. All the other wires are essentially outside of the field. So this is part A. Now part B asks us to find the torque on the coil. Well, we're going to use our torque coil formula. So we have a formula for the torque on a coil. It's the number of turns times the current times the area of the loop times the strength of the field times sine of the angle. Now this angle, just as a reminder, is the angle between the field vector and the surface normal. So this coil is laying flat. That means its surface normal points directly up. So initially in this situation, that theta is going to be 90. Right? Theta is 90 at the start. So this tells us that torque on the coil is going to be equal to the number of turns, which is 40, times the current, which is 1.5, times the area, which is the product of the width and the length, 0.06 times 0.04, times the field, which is 0.05, times sine of 90, which is 1, times 1. If we plug this all in, we get torque on the coil is going to be 7.2 times 10 to the minus 3 Newton meters. So this is our calculated torque on the coil. And then the third part of this question asks us to find the direction of rotation. Well, we can just do this by picking an arbitrary point and working out what's happening. We will pick a point over here between C and D. The current is heading away from C towards D. The field is heading towards south. So you get your right hand, point your index finger, middle finger, and thumb all at 90-degree angles to one another. Index finger points in the current, middle finger points in the field, our thumb points up. That means the force is going up on this side. This implies the force must be going down on the other side. So if our viewing eye is here, looking at this, and this is our axis of rotation, this is going to spin counterclockwise. So therefore, the rotation will be counterclockwise. And this is how we do this question.